Hello, everyone, and thank you for attending today's webinar. Wiley is committed to lifelong learning, and we are pleased to partner with the World Federation of Science Journalists and the Association of Healthcare Journalists to offer Science Talks, an educational webinar series for journalists around the world. Today's complimentary one-hour session, Science Talks with the Society of Environmental Toxicology and Chemistry, What Journalists Should Know About the Environmental Impact of Microplastics, is brought to you by the Wiley Network. Before we begin, we wanted to cover a few housekeeping items. At the bottom of your audience console are multiple application widgets you can use. If you have any questions during the webcast, you can click on the Q&A widget at the bottom and submit your question. We will try to answer these during the webcast, but if a fuller answer is needed or we run out of time, it will be answered later via email. We do capture all questions. You can expand your slide area by clicking on the maximize icon on the top right or by dragging the bottom right corner of the slide area. If you have any technical difficulties, please click on the help widget. It has a question mark icon and covers common technical issues. An on-demand version of the webinar will be available approximately 1 day after the webcast and can be accessed using the same audience link that was sent to you earlier. With those housekeeping items out of the way, we will begin today's webinar. Today's session is brought to you in partnership with the Society of Environmental Toxicology and Chemistry. SETAC has a mission to support and facilitate the development of principles and practices for the protection and enhancement and management of sustainable environmental quality and ecosystem integrity. SETAC operates upon a set of founding principles which are multidisciplinary approaches to solving environmental problems, balance and participation involving stakeholders from all sectors across academia, government, business, nonprofits, and NGOs, and science-based objectivity. Our speakers for today's webinar are Dr. Suzanne Brander, faculty in the Department of Environmental Toxicology and Chemistry at Oregon State University. Dr. Brander's research encompasses the fields of toxicology, endocrinology, and ecology, integrating molecular approaches with measurements at the organism and population level. Her main focus is on the effects of stressors such as emerging pollutants, plastics, and climate change on aquatic organisms, but her research and teaching spans the links between ecological and human health. She received a PhD in toxicology and pharmacology from UC Davis in 2011, following an MS in environmental science and policy from Johns Hopkins University and a BS from Elizabethtown College. Dr. Brander has been involved in the Society of Environmental Toxicology and Chemistry since 2005 and is now a member of the SETAC North American Board of Directors. Recently, Brander and colleagues started a new global SETAC interest group on microplastics research, which is comprised of research professionals working on plastic pollution from academia, government, industry, and the nonprofit sector. Brander currently leads research projects on microplastic occurrences and effects in commercial fisheries on both the east and west coasts of the United States, and is funded by the National Oceanic and Atmospheric Administration, as well as the Environmental Protection Agency. Dr. John W. Davis is a senior environmental scientist and consultant at the Dow Chemical Company and has over 30 years' experience in leading environmental sciences research and safety testing. In his role, he provides leadership to Dow's businesses on the environmental issues that support the safety of Dow products and manufacturing operations throughout their life cycle. These efforts include working with Dow businesses on the development of new chemical alternatives with improved sustainable environmental profiles. His past research interests include an active laboratory-based program focused on the environmental risk posed by PBT chemicals. More recently, Dr. Davis has been focusing his activities to meet the increasing need for scientific-based evidence for the regulations, restrictions, and environmental safety assessment of polymers, plastics, and microplastics. In his role, he provides scientific leadership to industry trade associations, including the International Council of Chemical Associations and the European Chemical Industry Council, as well as with Dow businesses to promote a risk-based framework for the safety evaluations of polymers and microplastics. These efforts are critical to Dow's plastic sustainability strategy and the promotion of safe materials and alternatives with improved sustainable environmental profiles. And with that, I will now turn things over to Suzanne and John for the presentation.
Yes, thank you, Josh. This is John Davis. I will start out, and then Suzanne will take the second half. And hello and good day to everybody on the line. When I was first approached to speak about this issue, the original topic was a webinar on microplastics. However, limiting the conversation to strictly microplastics provides only one component of the larger and more encompassing issue, which is plastics in the environment. So in today's webinar, Suzanne and I are going to expand the conversation to provide you with a more holistic view surrounding microplastics, and that's why the webinar is titled Microplastics in the Environment. So let me go to the... Here are the elements of today's the agenda. This slide is titled Agenda. These are the different elements of today's discussion. I would say the bulk of the discussion will be on the first two bullets. We'll start with definition and sources. And the reason is this terminology around microplastic has been very muddled. And people have been discussing definitions for about the last 3 years, what is and what is not a microplastic. And they still haven't reached complete consensus. However, the definition is starting to take shape a little bit in the European Union, where they have proposed strict regulatory definitions laid out in their proposed microplastic restriction regulation. But today we're going to use more operational definitions as to not to limit our discussion and to understand how these terms are used interchangeably by people. They'll also be speaking a lot about exposure and effects of microplastics, and exposure and effects is the definition of risk. We'll also be interspersing in different areas research needs in the area of microplastics, and that's because from a scientific perspective, we are still in the early stages of our understanding of the environmental impact of microplastics, as well as having reliable data to make decisions. So this is a really blossoming area and important. Management, we'll talk in specific areas on efforts going on to mitigate the leakage of plastics into the environment and what people are trying to do and attempting to do. And then some sources that will be in our presentations as well as the brief at the end. So with that, we'll start. The first slide is titled Increasing Global Demand for Plastics, so hopefully everyone's seeing that slide. And the point of this slide is plastic production now and in the past. And global plastic production has increased dramatically since about in the early 1950s when it started to about 9% a year. And with 2015 data, the current production was 388 million tons of plastic produced, almost all of it from petro-based sources. Now, many polymers are produced from these, and I'm only going to mention these once, but there's 6 main polymers that we're talking about. There's polypropylene, the polyethylenes, including low density, low linear density, and high density polyethylene. There is polyvinyl chloride and polyethylene terephthalate. That's the last time I'm really going to mention them by name, but those are the 6 major plastics, although there are many other polymers that people may lump into the microplastic arena. So that's the production. A lot going on. Well, if you have production of a material, you have waste. This slide, called Plastic Use and Disposal, is to illustrate the waste generated from plastic production, the amount now being produced and the amount predicted in the future. If you look at the bottom of the figure, you have a timeline from 1950 to 2050, about 100 years. Plastic production started in the early 50s, and the solid lines are actual data from past production, and the dotted parts of the line are those predictions of what's going to occur in the future. So as you can see, between 2010 and 2020, the data goes from solid to dotted. So the point of this slide is plastic waste will continue to increase significantly for the next 30-plus years as following plastic production. That is if we keep everything as is, that is business as usual, and don't change our habits. The way we handle plastic waste also just falls off. How we dispose of it, how we incinerate, recycle it. So you can see this large gap between the waste produced and our handling, right? And that is the amount of waste that could go into the ocean and the environment. So the point here is we need to start doing something different if we want to manage plastic waste. So what is plastic waste? Let's start talking about the terminology of plastic waste. Plastic waste includes all sizes of residues, from largely visible and easily removable items, which you see on the left, to smaller and more to small items that are hardly seen to invisible, called microplastics. So the macroplastics, this will be the term. You can see the bottles, the jugs. These are what we refer to as macroplastic. Microplastics are plastic particles that are smaller than 5 millimeters in width or length. These, and we'll talk more about that, but that's the difference. I think I've titled this definition. Now we're on to slide 10, definition and sources. This is just, I think definition is really too strong of a word when applied to microplastics issues. So I don't like to really refer to it as acceptable terms of reference at this point in time, because people are always discussing, arguing definitions. But there's some general terms that people use. First, I have this umbrella because microplastics, and now we're just talking about microplastics. Microplastics are a very diverse set of materials, and they fall under a large umbrella. You're talking about different particle sizes. The particle sizes range from 5 millimeters to some people to 1 nanometer. That's over 6 orders of magnitude, or a million-fold difference in sizes. The shapes can be different. They can be spherical, they can be irregular shaped, or they could be fibers. And there could be different chemistries, different polymer types. I mentioned the 6 major polymers, but there's dozens and dozens of additional polymers where people are considering whether or not they should fall under the plastic waste issue. I also put I have the difficulty personally in visualizing different sizes below what I can see. So 5 millimeters or 5 microns or 5 nanometers. Intellectually, I understand them, but it's hard for me to visualize. So I put this U.S. penny on the screen to show what size of the largest size microplastic. And the U.S. penny is 19 millimeters in diameter. And microplastic particles, the largest one, are 5 millimeters, so about a quarter the size of a penny. And then they go down about a millionfold in size. So that just kind of helped me to conceptualize what microplastics are. So now let's come into the microplastic terms, because microplastic terms are really, they categorize different types of microplastics based upon the sources and how they enter the environment. And again, these are more operational definitions. There's no glossary of terms that you could go to, and which makes it a little bit confusing, especially in publications or the media or even in the scientific articles on the terminology. But with that, so we have one type of microplastic that originates from the macroplastic. You have a macroplastic. The current term they're using, the plastics going into the environment, is leakage. because there's different ways plastics get into the environment. There's different leakage points, but somehow it gets into the environment, and we'll talk a bit more how. Once it's in the environment, the material, these larger plastic particles, they fragment and degradation occurs due to what they call weathering of plastics. And this weathering comes from sunlight, wind, water, mechanical action. And then they fragment into smaller pieces. And once these pieces become less than 5 millimeters, they are called microplastics. And the term that you will hear often is these are secondary microplastics because they didn't enter the environment as microplastics, but they fragmented. So you'll hear that term secondary microplastics. Well, if they're secondary microplastics, there must be primary. And indeed there are. Primary microplastics are particles that are directly released into the environment as small plastic particles, that is at 5 millimeters or smaller. And a lot of times these are originally manufactured to be that size and purposely used for particular industrial or domestic applications, such as exfoliating facial scrubs, toothpaste, or abrasive blasting. However, there are and those were referred to as microplastics or primary microplastics. However, there's another source of microplastics also, and that is materials that enter the environment as small fibers, usually from washing of textiles, and these are referred to as microfibers. You'll hear people refer to them as microfibers, but oftentimes they are lumped into primary microplastics too when making assessments. So people will ask me, well, is a microfiber a microplastic? And the answer is most people consider them in the same category. But again, the source is different. So now you can starting to straighten out the terminology here. I just put another slide in here. Now we're showing size does matter, just to give, again, a visual representation of what we're talking about. Again, on the left-hand side, we see some materials made from synthetic material plastics. These happen to be fishing nets, but there's a lot of other marine type of materials that are used in the marine environment that break down. But what I really want to focus on is on the right side. Here is different sizes of microplastic ranging from 5 millimeters, which is the largest on the left-hand side in the vial, down to 0.5 millimeters. Now you see this is only a 10-fold reduction in size from left to right. Microplastics extend down another 100,000-fold in size to the nano. So you can see how identifying these particles, these smaller particles in the nano and the small micro range is difficult. But this starts giving you an idea of what we're talking about visually. Okay, so now we got an idea of the terminology. We've talked about production. We've talked about plastic waste. We've talked about leakage. Now, how do plastics get into the environment? This slide is titled Plastics Lost to the Value Chain. And it was taken by an excellent article that was put out in the United Nations Environmental Program, and it's referenced here. And what it does is you look at this from left to right. This is the value chain for plastics. So annually, and this is the kind of the gold standard for how much plastics are getting into the environment, 8 million metric tons on a global scale in 2015. And there are different ways that plastics leakage or get into the environment. If you look on the left-hand side, you see the raw material, the polymer production, the plastic conversion, and production of plastic product. Those are all the manufacturing sections. Materials do leak into the environment there. However, then you hit in the middle, this one with the circle says use. This is the consumer use. You have the consumer use, and then you have the end after the application, after the use of the material, it's disposed of and either collected, sorted, landfilled, or recycled, and then that's the end of life. what we call the two major leakage points are the use and end of life. Now, the manufacturing, there is leakage all the way through the value chain, and these are a little bit easier to address because they're point sources. But here are the major, what we call hot spots, use and end of life. And there's a lot of activity going on around the world to address these two areas on preventing leakage of materials into the environment. And I'm not going to talk about that today, but there's a lot of information you can go out and even look in the European Union's document on the circular economy, and they go over that. So now this is how plastics get into the environment. So now the next slide, sources of plastic to the environment. So we know that in 2015, the value people are using now, and you'll see this at its pretty reliable value at this point in time, of 8 million tons. And 64% of that going into the environment is in the form of macroplastics. And 36% of this is in the form of microplastics. Oh, I need to point out this reference on where this information comes from. These numbers represent our best knowledge or current knowledge to date. And a year from now, as we get more data, they'll probably change. But right now, this document put out by UNEP, the United Nations Environment Program, was a study they contracted the Technical University of Denmark to do to look at the leakage of plastics into the environment. So these come from that document and represent the best that we know to date. 2 years from now, we'll look at these and probably say, we missed the mark, but this is what we know right now. So anyway, 64% of that comes from macroplastics and 36% from micro. It's basically 2/3 and 1/3. But as we know, when macroplastics get in the environment, they break down to microplastics too, so that we already spoke about that. So on macroplastics, what we have here is some of the major sources. They had listed about 7 or 8 sources, but I just put the major sources that they identified. One was littering, which surprised me. I didn't realize littering, that was a surprise to me. 10% of the macroplastics leakage is from littering. Only 7% comes from fishing nets and related paraphernalia that are used in the marine environment. Are macroplastic, and the large percent, which is this was pretty well accepted regardless how the number changes, is from mismanaged waste treatment. The material is not disposed of correctly. It is the largest source of macroplastics. I'm adding another. I'm going to adding the animation for the microplastics. Here is again, a third of the material is microplastic, and that's entering the environment. Again, here what we have is some of the top. I have the top actually 4 and plus one another. There's about 8 or 9 that they had in the report. But tire abrasion and textile and road markings are actually the major sources of microplastics into the environment. You can see they represent pretty much, what is that, 27% of that 36% there. So they're major. City dust, which was a new one to me, represented 7%, very large, even more than the fibers. I wanted to point out microbeads from home and personal care, because this is what has gotten a lot of attention, especially in the United States. But a lot of this kind of started off the microplastic awareness was the materials in home and personal care, only about 0.2%, but a source. So, where are the plastics? Well, this is, let me go on. As you've heard, the plastics have been found in all environmental compartments. This slide's on here because it showed that there's not a part on the planet, at least the surface, where we had not found plastic waste or plastics in the organisms. And this was an article in 2017 by Jameson, where they found plastics in the Mariana Trench. Now, for those who are not familiar with the Mariana Trench, it's located in the Pacific Ocean, and it's the deepest natural trench in the world. It goes down to about 11,000 meters. So even there, they found a plastic bag laying on the bottom, as well as plastics in some of the organisms there. So plastics being produced since the 50s, so waste it can be found everywhere. Next, the next was detecting microplastics in the environment. However, what we're most familiar with in the news over the past several years is the monitoring of our rivers, oceans, and beaches, and finding microplastics there, even on land, due to the application of biosolids. And even in our food, I have seafood here, but even in our drinking waters. And this is what's really a lot of the monitoring and reports have been about. And the leakage of plastic waste into our environment is definitely something everyone wants to minimize. And we've been monitoring and measuring macroplastics in the environment going on now for the last several decades, and we're pretty good at doing that. Or at least they even have apps and databases and processes in place to help monitor macro. However, monitoring and measuring microplastics in the environment is a relatively new endeavor, and has really suffered from the lack of analytical methods for detection and identification of very small pieces of plastics. So I just want to talk a little bit about that. Really, on this here, we're talking about identifying and quantifying microplastics in the environment. That's what I refer to as environmental monitoring. And up until 3 or 4 years ago, monitoring of microplastics was done primarily visually, and sometimes using magnification. And I would say really monitor. I know there's reports from many years ago, but the effort started in monitoring microplastics around 2010, 2011. And then people realized that it was not optimal doing it this way, but there was no standardized methods available. We had multiple matrices that we were trying to analyze, such as we saw before. We had soil, we had sludge, we had water, we had food. And the methods were not available, and they were expensive to develop, and the tools weren't really identified of which were the best tools. So as a result, a lot of the early monitoring data, we don't have a lot of information on smaller particles, the below 0.1 millimeters or less than 100 microns. So we don't really know much about those and their prevalence in the environment. And then what they found out also later is they started developing better methods. The earlier reports demonstrated the visual observation. There were larger error rates in both identification and quantification. So in the last, I would say, 2 to 4 years, significant effort has been made in developing better analytical methods. And this has been done using improved imaging technology, so you can identify particles, and then coupling this to spectrometric analysis using some analytical instrumentation. So basically you can identify the particle visually with the imaging technology, and then the instrumentation can give you a fingerprint of that particle, which you see here, to tell you what type of plastic it is. And these techniques are just coming available, and I'm really excited for the next couple of years to start to see if we'll be able to start getting really higher quality data on where the plastics are, what the sizes are in the environment. So better technology and better methods equal better data. And then the last slide I have here, we come full circle back to the areas of plastic concentration. As we saw, 8 million tons go into the water into the environment every year. Again, though, that's on a global scale, and those are not homogeneously distributed. There are areas of plastic concentrations that are what we call that have the hot spots. That includes landfills, land that use agricultural land. Also, this materials collected estuary near urban areas. And plastics are a particular threat to marine ecosystems because oceans and seas are the final dumping ground for flowing waters carrying plastic trash. And most of the losses, as we saw, are unintentional diffusive losses that cannot easily be solved by what we call end-of-the-pipes solutions. So losses from product use and maintenance must be addressed from more a global producer-consumer perspective. And the banning of microbeads from cosmetic is an illustrative action for helping solve the problem, but it doesn't solve the wider problem. So we need to be paying attention to and not overlooking a lot of the other sources. And with that, I will turn it over to Suzanne.
Good morning, everyone, and thank you for attending the webinar this morning. I'm going to take over, like John said, and talk a bit about exposure and effects and some of the challenges that scientists and research are facing in studying microplastics. And then I'll finish up talking a bit about management and how we're trying to start to stem the tide a bit of plastics being input into the environment. So as far as exposure and effects go, I'll start out talking a bit about macroplastics and then delve into microplastics. Although, of course, as John said, plastic pollution is found everywhere, including some of the most remote places on the world, plastics in the marine environment have really received the most attention thus far. Oceans are estimated to contain between 7,000 and 25,000 tons of plastic that's been input, since we started manufacturing plastics, like you said, in the 50s. And much of this concentrates in oceanic gyres. There are 5 of these, and these form due to ocean currents and wind patterns. Pictured here on slide 19 is a fish called the rainbow runner, and I'm going to show a couple of specific examples in these next few slides. This fish was captured a couple of years ago from one of the oceanic gyres, and it had consumed about 17 plastic fragments, which you can see below the body here after it's been dissected. These are also known as Spanish jacks. They're found in the tropics and subtropics, and it's a predatory fish, but it's commonly eaten as seafood. And so this has become a concern over the past five or so years, in that we're finding plastics in seafood that's commonly ingested by humans. Researchers will go to fish markets and pick up fish from the table and find plastics in some of these fish that are being consumed for human food. So there are a number of different reasons for concern. I mean, one of the most obvious concerns is that these plastics are going to obstruct the digestive tract of the organism that consumes it, if they're a fish, squid, what have you. But plastics can also contain or associate with chemicals that are either in the water present from runoff or are used as plasticizers in the manufacturing of plastics. And there is some debate as to whether the chemicals can leach off into the tissue of the organism or whether it increases their exposure. And that's something that's still being studied. So a lot of the recent emphasis, of course, has been on microplastics, but I wanted to talk a bit more about macroplastics. As you can see here, I pictured a few examples, and thousands of aquatic organisms have been documented to either ingest or become entangled in marine debris. Pictured here, the birds you see here on the slide, that's been opened up is a Laysan albatross. These are birds that live on Midway Atoll, and this is a group of islands in northwest Hawaii. It's called Midway Atoll because it's in the middle, literally the middle of the Pacific Ocean. They're large birds. Their wingspan is about 6 feet. They can live for half a century or more. And plastics are carried to these remote areas that they live by ocean currents. So the adults are vulnerable because they forage for food that floats on the surface of the ocean, and they kind of skim the surface with their beaks, pick up anything that's on the surface, and then come back and feed that to their chicks. And these, in a way, the albatross were kind of the canary in the coal mine for the plastic problem, because researchers started to find chicks that contained plastic obstructing their digestive tract, and then they would realize as they were fledging, and they typically will kind of spit up what the squid beaks and other things that they can't digest, before they start to they take off and fledge, we were finding chunks of plastic in what they were leaving behind in the nest areas. Other larger animals impacted by plastics, of course, are sea turtles. A recent study that just came out at the end of last year indicated that for younger sea turtles, if they ingest a little more than a dozen pieces of plastic, which is about what we saw that fish had ingested in the earlier slide, that can be lethal to them. And they are also documented to mistake plastics for prey, so plastic bags can look like jellyfish, for example. It's estimated in that recent study that about half of all sea turtles worldwide have ingested plastic debris. If you look at how much plastic is out there and how often sea turtles are documented to have encountered it. It can block the digestive tract. It can also, if it's a sharp piece of plastic, it can perforate soft tissues like the wall of the intestines. Last megafauna example I'm going to give here are whales. Whales, of course, are charismatic megafauna. Everyone notices when a whale beached and they want to know what happened to it. Well, recently we're finding that a lot of whales have been found to ingest larger plastics. They're also filter feeders, which is going to allow me to segue into microplastic concerns. And so a large animal like a baleen whale filters zooplankton, so small creatures out of the ocean as food. And it's filtering zooplankton, it's also filtering microplastics into its digestive tract. This whale pictured here was beached last year in Indonesia. It contained a pair of flip-flops, also a number of those kind of solo-sized red drinking cups as well. So getting on to microplastics. Microplastics are a newer area of research, and like John said, we're still in the early stages of a lot of this. And also, like you said, they're smaller than 5 millimeters, but they go down to the nano-size range. Nanoparticles are, for example, being used for pharmaceutical purposes for drug delivery. So those are being produced in higher and higher quantities as well. Pictured here on slide 21 is the inside of a shore crab. And this is from a recent study that was published in Environmental Science and Technology, where some scientists looked at how animals, aquatic animals, were uptaking microplastics. And it turned out that for crabs, just like other animals, they ingest them with their food. They ingest them because their prey already contain microplastics, but they're also ventilating the plastics. And so as they're acquiring oxygen from the water, they're also breathing in, essentially, microplastics that then get caught in the gills. And those can be difficult to remove. What these researchers found is that it took longer for the crabs to eject these particles from their gills than it did for them to excrete particles they had eaten with their food. And so that's another new area of concern, because if animals are getting plastic particles caught in their gills, it can affect their ability to respire, to acquire oxygen, which affects all of their other life processes. So to sum up the effects of microplastics, as you can see, they can be inhaled, which isn't always something we think about when you think about an animal living in water, but that's how they get their oxygen, by getting oxygen through the gills. They can translocate to internal organs if small enough. There was a study in herring that came out recently showing that small microplastics under about 100 micron in size can be translocated to tissues like the liver, for example. They can stunt growth. So if you have a large number of plastics in the gut, in the digestive tract, that is interfering with other nutrients that the animal can obtain from its food. It feels full. It may not forage or eat as much. And so that can affect their growth. It can cause stress, and organs like the liver, for example, it can cause reproductive stress. It impedes other bodily functions. If you're dealing with a acute stressor, you're not going to be doing other things like looking for food or looking for a mate, for example, or it may impede your ability to swim as quickly. And it occurs across food webs, beginning at the bottom of the food chain. And so thinking about the food chain, looking at slide 23 here, we're starting to think a lot about the biotransfer of microplastics. And I think something we tend to forget is that as humans, we are also part of that food chain, and we're really at the top of it. So looking at this graphic, you see in number 1, the little randomly sized ovals here are representing microplastics. In box 2, you're seeing zooplankton that have taken up those microplastics. So these are small aquatic animals like copepods and shrimp that are then eaten by smaller fish in 3, which of course then the smaller fish are eaten by larger fish, like that rainbow runner we saw in the earlier slide. And then those larger fish end up on our dinner plate. And we're still, there aren't a lot of studies on human exposure to plastics. We don't know yet what effects plastics have on humans at the current rate of ingestion. And the current rate of ingestion is relatively low, but a recent study estimated that people who eat a lot of shellfish, which shellfish are filter feeders, so they're filtering water. As they're filtering water to get their food, they're also taking up plastics. That people may eat as many as 11,000 pieces of small microscopic plastic annually. They've also been documented in human excrement. And a concern is that if microplastics can translocate from the gut of aquatic organisms to other tissues, there's also a chance they could do that in humans as well. So that's an area of ongoing research. And really right now the physical presence of plastics is a bigger concern than their chemical components. So getting to the in a nutshell slide, plastic production, like John mentioned as well, is predicted to increase exponentially over the next several decades. Plastics are finding their way into the environment through wind and water. They're distributed across the globe. They accumulate in landfills and coastal zones and agricultural fields. When we use biosolids, we're taking those solids from wastewater treatment and applying them to other locations. And both macroplastics and microplastics can be physically harmful to wildlife. The smaller the animal is, the more macro a microplastic is going to be, like we saw with the worm that was captured from the Mariana Trench. That worm was probably a few millimeters long. So a microplastic to an animal like that is really more macro than we would imagine or be able to visualize. So research on microplastic effects is ongoing. It's a huge area of research across the world. And and really what we're finding as we're researching the effects of plastics is that also that once plastics are out in the environment, it's really not possible to effectively remove them. And so you may have heard the recent news about the Great Ocean Cleanup, which was envisioned by Boy and Slat. This device that was designed to go out and collect plastics from oceanic gyres, which are pictured here on slide 25. It unfortunately fell apart on its first voyage. And so he had this vision that we could go out and clean up the ocean, kind of suck out all the plastics we had deposited, but it's really turning out to be a huge challenge. And so when it comes to management, we really are starting to look more at limiting the inputs of plastic. That's summing up research needs on slide 26. We really are focusing heavily on standardizing sampling and analytical methods. And also, like John said, the analytical methods are advancing quickly. We're more easily able to determine what types of plastics we're finding, and we're able to determine that at smaller and smaller sizes. We're working on figuring out what environmentally relevant concentrations are. This is challenging with small plastics because it's hard to sample them. It's hard to sample them in large enough numbers to get an accurate idea of what's out there. We're trying to measure effects in organisms in the lab at these environmentally relevant concentrations. And another huge challenge and need is identifying the most cost-effective wastewater treatment methods. So in California, for example, wastewater treatment plants have been tasked with trying to better control the amount of plastic that's arriving in waterways from effluent. So lots of research challenges, and I just show on slide 27 kind of a breakdown of what plastic researchers are facing in my lab and in labs across the world. But finding out how much plastic is in the environment is challenging. You have to think about how you're going to extract it, what kind of net are you going to use, what size pores is the net going to have, because that's going to determine how much of the plastic you can capture. How are you going to enumerate it? How are you going to count how much is there? What microscopes, what approaches are you going to need to use? What analytical equipment are you going to need? It takes a lot of time and funding to really do a study like this and to do it well. But on the management side, we're really trying to rethink plastics, and this I think is happening globally right now. Trying to redesign and innovate and make things easier to recycle. Try to improve waste collection, use more reusable packaging. Packaging is a huge component of the plastic waste we produce on an annual basis. Countries really need to come together to establish a global protocol. And part of the challenge with recycling is that we don't have viable markets for all types of plastic. I live in Oregon, and a recent development was that we're no longer able to recycle a large number of the plastics that we use because markets in Asia have stopped taking a lot of those plastics. And so I think we're reaching a point where we need to really rethink where those viable markets are and how we can produce plastics that can be more easily reused and biodegraded as well. A recent development is a pilot program called Loop, which was started by a company called TerraCycle. And what they're trying to do is to reduce the use of disposable plastics by producing containers that contain typically used products like your favorite ice cream, for example, pictured here, or deodorant or other personal care products. They deliver this box of products to your door. You use them. You put them back in the box when you're done, send them back, and they rinse out the containers and refill them. And this program is being piloted in Paris and New York in the coming year, and they're hoping to expand it. So in addition to trying to reduce use of things like plastic bags and straws, programs like this are being tested out to try to reduce the overall input of plastics in the long run and to reduce the number of plastics that need to be recycled, which is turning out to be a challenge. So I'm going to finish up there, and John and I are happy to take questions. I think we have about 12 minutes left, and I'll also mention that following our presentation, there will be an informational brief produced by Wiley available on micro and macroplastics, as well as a virtual issue that will include articles published by Wiley. That will be available to all of you. Thank you.
Thank you, Suzanne and John. And with that, I'll begin our Q&A part. My name is Catherine, and I'll be reading the questions out loud. Our first question I'll push to the slide area. And this is, how fast can replacements spread, such as biodegradable materials in cloth, tires, and road markings?
Oh, Suzanne, can I take that one? Start on?
Yeah, absolutely.
Okay. This is John again. This happens to be one of my areas of particular interest over the years, is biodegradable materials. There's really two components to this answer. One is, first you have to have a biodegradable material that you need to substitute for a specific application, whether it be in clothes, tires, or road markings. So there's the how long does it take to develop that? And then once you have a material, how you substitute it within the specific application? How long does it take to substitute a specific application? So first is to say that this is an area of active research by people in industry is looking at biodegradable materials. The point being, though, biodegradable is not an inherent property of a chemical. It's more of a action that occurs once it's in the environment. So how you classify something biodegradable. There's not really a lot of biodegradable materials for specific that can be drop-in replacements, but they're looking into them. So that answer could be if years to months to years to find the right material. The second aspect is the implementation. Once you have a material, how long does it take to implement it integrate it into the value chain, as we saw before? For some things, maybe for clothing and road markings, it may take less time, a couple years. For other materials such as food packaging, other may take longer because there are regulatory pressure. So we're talking about years usually, and I can't say 5 years, 6 years, 10 years, but development of the material and then integrating into the value chain. I'll give you an example. We've came up with a material for a sustainable flame retardant to be substituted into plastics. It took us 4 to 7 years to develop the material, and then 3 to 5 years to integrate it into the value chain. So it's not an easy process. Mm-hmm. And so we'll go with that. But it is an area of interest. I think it's one aspect of tackling the plastics in the environment is to make them more benign. What people are really doing a lot now is focusing on using post-consumer recyclable plastic in products and increasing that. That's been it looks like a larger growth area of recycling more and then developing products from post-consumer recyclable waste.
Mm-hmm.
Suzanne?
Just to add to that answer, as far as your question about biodegradable materials and cloth, and like John said, that's a huge challenge, and it takes years to develop just one product. But there is a solution to all of the microfibers that are coming out of our say just regular washing water that goes out into the environment daily, and there are filters that you can purchase for your washing machine that actually capture a lot of that material, be it if it's synthetic or even if it's cotton fibers that are getting into the environment. So there are ways to control inputs as we're waiting for better alternatives to come on the market.
Thank you, John and Suzanne. Our next question is the reduction of production discussed within the industry at all instead of growth as projected?
I think that would be a question for John.
Reduction of production. I think smarter use. I think more the focus has been smarter applications and uses, and then of production rather than limiting. I haven't seen. I can't really speak for all industries because it's a global industries in North America, Europe, China, and I don't see you saw the projected production numbers, so there may be a slower down, if we change in that, but I still continue to see as developing countries emerge and people they increase their use of plastics. So that's more a socioeconomic question than a scientific.
It at least seems that with programs like Loop, even if we're not reducing production, maybe some companies are thinking about changing the way they produce products so they have a bit less of an impact on the environment.
Yeah, and that's exactly right. And that's a good point, Suzanne. I know we're working Dow, I'm using us as an example, are working with our packaging companies to help them make their products more susceptible to recycling, and helping them, and they're working with us to identify what's keeping these things from being recycled, how can we increase the recyclability of these materials so that we can capture the waste or the material and get it back into new products. So we're definitely, those have been the biggest areas of focus because those are the more immediate, I think, I would call not low-hanging fruit, but where we could stop the leakage first while we work on solutions, as you were saying, Susan.
Yep, absolutely.
Great, thank you both. Our next question is, I was amazed to see the quantity of microplastic waste that comes from tire degradation. Can anything be done to deal with that, either in manufacture or in cleaning up?
I will start that since I put that up there. First, you have to understand that our expertise is in the science of this. We're getting into really socioeconomic questions. So right now, our expertise is dwindling in that area and becoming more opinions. So when we start addressing questions like this, so this is my opinion, and I think, of course, there is something to do. The tire manufacturers are already looking into that. I mean, they're getting pressure into understanding how tires wear, how to prevent them, and nobody realized. I think I put that up there because I'm glad you said it surprised you, because I think it surprised a lot of people that tires are a major source, and they're not easy to ban as cosmetics. I think people need their tires a lot more. So I think the manufacturers of tires, and I don't really know. I know that they have been working on it. They're aware of the issue. They're looking at studying how they wear. How do you measure tire wear? How do you measure how many particles are produced? What are the new products you could put in to increase the wear? Increase the lifespan. So yes, they're working on it, but I don't have any more information than that. I think identifying the issue and the sources starts leading towards developing solutions by different sectors and different industries. That's why it's so important to understand. Okay, go ahead. Sorry.
I was just going to say, add to, and when it comes to problems like what we're seeing with tire fragmentation and degradation, changing the way tires are manufactured is going to do a lot more to solve the problem or to reduce the problem than trying to clean it up in the aftermath. Because those particles end up in stormwater runoff, and you can catch some of that in drainage or by having better catchment designs. But it becomes much more challenging when you're trying to tackle it after the fact than it would be to change the way the materials used to make the tires.
That's great. Thank you. Our last question for today is, do you recommend any resources that journalists can use when reporting on microplastics?
As far as resources to use when reporting on microplastics, I think that the brief that was produced by Wiley to accompany this webinar, as well as the virtual issue that's going to be produced, are both excellent resources to start. The UN Environment Program and the NOAA, the National Oceanic and Atmospheric Marine Debris Program, are also both excellent resources for documents and publications on recent research and recent findings on macro and microplastics.
And I agree with that, Suzanne. And to point out, it's best to go to established, sometimes they're a little slower, but established resources with strong credibility to get the information. You're just not safer, but they have more transparency, and they have credibility. Not that they can't be wrong, but they have historically have a strong credibility to all those organizations that Suzanne just mentioned.
Mm-hmm. Yeah.
Wonderful. Well, thank you, Dr. Brander and Dr. Davis. We appreciate you sharing your expertise with us today. But I think this is all the time we have. On behalf of my colleagues here at Wiley and and our partners at WFSJ and AHCJ. I'd like to thank everyone for attending. Your feedback is very important to us, so please do fill out the attendee survey, which we use to enhance future sessions of Science Talks. A video of today's webinar will be made available with links to additional resources. If you do have any further questions, please email us at newsroom@wiley.com. Our next Science Talks webinar is scheduled for Tuesday, March 19th, 2019, and will cover sustainable agriculture. We'll be sending out registration details shortly, so be on the lookout. Once again, thank you everyone for your time.
Thank you.
Thank you.